So now we'll discuss making inferences about two means when they come from dependent samples. All right, so in this case, our data set is going to consist of matched pairs of data. So as an example, you could have one matched pair representing a particular person's weight before and after some weight loss program. So for instance, it could be that they weighed 205 pounds before the weight loss treatment and let's say 185 pounds after the weight loss treatment. And your entire data set would consist of these matched pairs. So for instance, the next matched pair may be 190, 190, and 180. And the next match pair may be uh, 195 and 196. So these match pairs each number, each coordinate of the matched pair actually represents a measurement before and after some treatment. So the first number in the match pair and the second number in the match pair are dependent on each other because it comes from the same person. And you'd have a lot of these match pairs. Let's say we have n of them. So there'd be n matched pairs. And what we're going to do is we're going to test a claim about the difference in the first and second coordinate of these matched pairs. And we're also going to create confidence interval estimates for the difference between the first and second coordinate of these matched pairs. So each one of the matched pairs has its own difference. So let's take a look at a notation. That difference in each individual matched pair is going to be denoted D. So for instance, the first difference, or the first D, would be this difference for this first match pair. We could call it D1, and it would be 200 minus 185, or 20. And for instance, the second match pair, the second difference, D2, would be 190 minus 180, or 10. And this third matched pair would have a difference of 195 minus 196, or negative 1. And we do this all the way until the nth match pair. There are going to be n match pairs. So we go all the way up to the nth match pair and find this difference, and it's going to be some subtraction also. Now, if we looked at the entire population of people who undergo this weight loss program, and we find the mean difference, or take all these differences and just find their mean, their arithmetic mean, then we would have the population difference, or the mean difference for the population. Since we only have sample data, we are not looking at the mean difference for the entire population. We're only looking at the mean difference for a sample. So that mean difference is going to be denoted d bar, and it's going to be the best point estimate we have for mu d. So d bar would be the mean value of the differences from the sample, and mu d would be the mean value of the differences for the entire population. SD is the standard deviation for the sample of differences, and n is the number of matched pairs in our data set. So those are going to be some of the notations we're going to use. Now let's take a look at some of the requirements. The first requirement is that the sample data are dependent. Basically, that you have matched pairs. There's some relationship between the first coordinate in a matched pair and the second coordinate in a matched pair. The second requirement is that the samples are simple random samples. And the third requirement is basically the requirement that the distribution is either a large enough sample or is approximately normal, which guarantees that we can use either the t or the z distribution, either the t or the z. And in this case, because we're only going to have the sample standard deviation of the differences, uh, we're going to use t for our test statistic. And this t test statistic is going to be found by taking the sample, the mean difference from the sample, and subtracting the mean difference hypothesized for the population, and dividing it by the standard deviation of the differences over the square root of n, where we're going to look at n minus 1 as being the number of degrees of freedom. All right, so That's going to be the test statistic we're going to use in order to do our hypothesis test. And when we set up our confidence interval, we're going to use d bar as our point estimate for mu d, and then we're going to set up our margin of error using this formula. All right. So now let's take a look at a few examples. For our first example, we'll take a look at this data set here, and we'll follow these directions for plugging the information into our TI 83 or 84 plus calculator. All right, so the directions read that we're supposed to use the data set. Um, oops, cancel. We're supposed to use the data set for exercise 5 and 6. Assume that you want to use a 5% significance level to test the claim that the paired data come from a population with the mean difference mu d equals 0. So we're testing the claim here that there's no difference in the paired data. And we want to part A, find the mean difference from the sample. Part B, find the standard deviation of the differences from the sample. Part C, to find the test statistic, and part D, to find the critical value. All right, so let's take a look. Let's plug this information into our trusty TI. Well, let's see how we get here first. Well, once you turn the TI on, you'll have it blinking on the home screen. You hit Stat, and then you will go to Edit, so you can edit your list. And once you're in the list, what you want to do is you want to enter your two data sets into list 1 and list 2. So I have the predicted high temperature forecast 3 days ahead, and I also have the predicted high temperature forecast 5 days ahead. And the 3 day forecast I put in list 1, and the 5 day forecast I put in list 2. And what I'm doing is I'm going to test the claim that there is no difference between the 3 day and 5 day predictions. So what I'm going to do is I'm going to take those lists, I'm going to go over to list 3, and I'm going to go up to highlight L3, and then it's going to ask me what I want to put in L3. Well, in L3, I want to take list 1 and subtract it from list 2, like it says to do here in the direction. So I'm going to type second, and then L1, and then I'm going to subtract from that, and I'm going to hit second and L2. So now when I press down or enter, this third column, L3, will give me the difference of list 1 and list 2. For instance, 79 minus 80 is -1, 86 minus 80 is 6, 79 minus 79 is 0. So list 3 is now the difference between list 1 and list 2. Okay, so over here I have my D's, or my differences. And what I want to do is I want to find the average difference from that sample, and I want to find the standard deviation of the differences. So I quit. Then I'm going to go over to Stat, the Stat button, highlight Tests. And now I am doing a t-test, because remember I'm doing a t-test statistic. So I go down to t-test. And once I go down to t-test, it's going to ask me if I have data or statistics. In this case, I have data, and my data is going to be actually in list 3. So I go down. This is what the null hypothesis is asking. The null hypothesis is that mu d is equal to 0. So this one is fine. I'm going to leave it equal to 0. And it asks me what list is my data in. Well, my data is not in list 1. My data is actually in list 3. So I highlight lists, and I change it to list 3 by hitting second and hitting the number 3 for list 3. The frequency of my data, well, all the data values have a frequency of 1, so I'm going to keep that the same. And now it says it's asking us for the alternative hypothesis. Well, since the null hypothesis is that mu d is equal to 0, the alternative is that mu d is different than 0, or mu d is not equal to 0. So I'm going to keep that highlighted. Then I just go down to calculate. I hit calculate. I see, let's see, of the things it's asking me. First, it asks for D bar, the mean difference. And the calculator doesn't know that we're doing differences, so the calculator is going to call it x bar because the calculator calls all data sets x. So x bar corresponds to d bar here. So the first question, part A, we were asked for d bar. D bar is actually what's being called here x bar, and d bar is 1.8. So d bar is equal to 1.8. That's part A, d bar. Part B, the standard deviation of the differences, S sub d. S with a subscript of d. Let's see what that one gives us. Alright, so that is actually going to be this standard deviation here, the sample standard deviation, which we see to be 2.77. So SD is 2.77. And C, the test statistic. C, the test statistic. Let's see. The test statistic is the t-score that was given up there, and that t is 1.450. So 1.450 is our test statistic. T is equal to 1.450. And the only other thing that would be left would be the critical values. But the critical values are found the same way as any other test statistic or any other T critical values. To find a T critical value, we go to table A3. We would look up the number of degrees of freedom would be n minus 1. In our case, it would be 5 minus 1 or 4 degrees of freedom, and then we just go to the column that had 0.05 in two tails. But we have enough here on our TI to actually make the determination of whether we should reject or fail to reject the null hypothesis based on just the p-value. And you see the p-value here is 0.22, which means we're probably going to fail to reject the null hypothesis. And the p-value method is the preferred method for our course. Anyway. All right, so that would be problem number 6. Let's take a look at a few more examples. Okay, and for the next set of examples, we are going to use these matched pairs of data, which represent the April body mass index and September body mass index of college students. So we have 1, 2, 3, 4, 5 college students, and we measured their freshmen actually, 5 college freshmen, and their body mass index was measured in April and then again in September. And we're going to use this data and a 5% significance level to test the claim that the mean change in body mass index for all students is equal to 0. So that is the claim, and it sounds like a null hypothesis. The null hypothesis in this case is that the mean difference in body mass index is equal to 0, which means that the alternative hypothesis is that the mean difference does not equal 0. And this is actually the claim. So we're testing the claim that the mean change in body mass index is 0. All right, now what we're going to do here is we're going to conduct a hypothesis test. We're going to have we're going to use the p-value method. So let's go ahead and do that. First, we're going to bring out our TI-83, and we're going to put each of these data sets into 2 lists. First, we're going to put the April BMI into list 1. So let's see how we get here. We would turn the calculator on. We would press stat, and we go to edit number 1 here, edit. And now we get to edit our lists. And in list 1, I'm going to put the April BMIs 20.15, 19.24, and so forth. And in list 2, I'm going to put the September BMIs. Now that I have all my BMIs from both data sets in my list 1 and list 2, what I'm going to do is I'm going to prepare the data by going to list 3, highlighting L3, and then I'm going to tell the calculator to make list 3 equal to second list 1 minus second list 2. So now list 3 is going to be the difference, the list of differences for each of the matched pairs. So here are all my differences. And now I'm going to do my hypothesis test. So I'm going to get out of here, second, quit. And when I quit, I'm going to go back over to stats, I'm going to go over to tests, and once again, I'm going to do a t-test because I don't know the population standard deviation for the differences. So I go down to 2, which is t-test. And once again, I don't have statistics. I don't have the mean and standard deviation and all that. I have data. So I go down. The null hypothesis says that the mean difference is 0, so that's good. My list is list 3, so that's also good. And the frequency of that list is 1. And my alternative hypothesis is that the mean is not equal to 0. So I highlight not equal to mu d. Then I go down to calculate. And I get, let's see here, I get a lot of information here. Oops. Let's go back to our TI there. So I get that the test statistic is negative 0.13, which is not extreme. That's less than one standard deviation lower, less than one standard deviation lower than the hypothesized mean of 0. The p-value is 90%, so there's a 90% probability of getting a sample this extreme if the difference is actually 0. And the standard deviation is given there as 0.84 or 0.85. So really, the most important thing here is the p-value, and the p-value is 90%. So let's put that up here. The p-value is equal to 0.90. And since that's greater than or equal to 0.05, we fail to reject the null hypothesis. Fail to reject null hypothesis. And let me see what that means in terms of the claim. Well, the null hypothesis is actually the claim here. So what we're doing is we're failing to reject the claim or the hypothesis that there's no difference in body mass index in September as opposed to April of your freshman year in college. So that whole freshman 20 pounds seems to be a myth based on this test. Now, number 10 is actually asking us to create a confidence interval estimate for the mean change in body mass index between April and September of the freshman year. So let's go ahead and do that. The confidence interval. So now, number 10, this is number 9. Number 9 is here. And now number 10 is the confidence interval. So number 10, let's see. Use the same data to construct a 95% confidence interval estimate of the change in BMI during the freshman year. Does the confidence interval include 0? All right, let's go ahead and do that. So let's bring back out our TI. So now we're going to go back where, well, let's turn it on first and clear it. We're going to go back to stat and we're going to go back over to test. But in this case, we're not going to do a t-test number 2. In this case, we're going to do a t-interval number 8. And once again, it's going to ask me if I have data or statistics. And in this case, I still have data. My data is still in list 3, so that's good. And we do want a 95% confidence interval, so everything is already set up. All I have to do is calculate. And upon the calculations, I get my interval to be negative 1.1 to positive 1.0. So negative 1.11 to positive 1.00. So that's my confidence interval. My confidence interval is negative 1.11 to positive 1.00. And that's my confidence interval estimate. So I would be 95% certain that this interval actually does contain the true difference in body mass index. And this interval does contain 0 because there's a negative number for the left endpoint and a positive number for the right endpoint. Because this interval includes 0, that means that 0 cannot be thrown out as a possible mean difference, which means there could possibly be no difference in the body mass index in April versus September of the freshman year.